Hello everyone, my name is Muhammad, and in this video I'll be explaining how social media detects influencers using graph centrality algorithms. Social media platforms like TikTok, Instagram, and Twitter rely heavily on identifying influential users. These aren't just users with many followers, but users who can spread information efficiently across the network. In this video, I'll be explaining how this problem is modeled using graph theory and how centrality algorithms such as degree centrality, betweenness centrality, and PageRank are used in real-world systems to detect influencers. I will also demonstrate these concepts visually using graph examples to show how different algorithms produce different results. The core problem we have here is identifying influence in a massive network. A social network can have millions or even billions of users, but they don't all contribute equally to the spread of information. There are three types of important users. First, highly connected users. These have many direct connections. Second, bridge users. These users connect different communities and groups. Third, authoritative users. These users have connections to other important users. This problem is critical for several applications. For example, in marketing, companies want to target users who can maximize the product exposure. In misinformation control, platforms want to detect users who can spread false information rapidly. And in recommendation systems, platforms want to prioritize content from influential users. The challenge is that influence isn't obvious. It cannot simply be measured by counting followers. Instead, we need a structured analysis over the network. This is where graph theory becomes essential. Okay, now for the graph modeling. I will now model a social network as a graph. Each user is represented as a node, also called a vertex. So these bubbles here are called nodes, also a vertex. And each relationship between users is represented as an edge. If the relationship is one directional, such as following someone, we'll use a directed edge. For example, here, if user A follows B, we draw an arrow from to B. Also, A follows C here. If the user interacts frequently, we can assign a weight to the edge, representing the strength of the interaction. Here we do have a graph consisting of nodes A, B, C until G, and many edges between them. This creates a structured network where information can flow through multiple paths. By modeling the system this way, we can now apply graph algorithms to analyze the importance of each node. Without this model, it would be impossible to systematically evaluate influence. The first centrality algorithm we will be discussing is going to be the degree centrality algorithm. This is the simplest centrality measure. It counts the number of connections each node has. For directed graphs, we can distinguish between in degree, which is the number of incoming edges, and out degree, which is the number of outgoing edges. Let's apply this to the graph. Node B, for example, has multiple incoming and outgoing edges. The in degree is 1, the out degree is 2. Node E, here, also connects to multiple nodes. The in degree is 2 and the out degree is 1. So these nodes would have higher degree centrality than other nodes. The assumption here is that nodes with more connections are more important. However, this method has a major limitation. It does not consider where those connections come from and where they lead to. A node connected to many unimportant nodes may still not be influential. So while degree centrality is fast and simple, it is not sufficient for identifying true influence. Another example I have here are two scenarios where both highlighted nodes in both scenarios have the same in degree and out degree. But if we compare, the influence of this node is much greater than this node. The second centrality algorithm we will be discussing is going to be betweenness centrality. This measures how often a node appears on the shortest path between other nodes. In other words, it identifies nodes that act as bridges in the network. Let's analyze the graph. If I want to send a message or information from node A to node G, the path goes through several intermediate nodes. If node E lies on many shortest paths, here is node E, if it lies on many shortest paths between different pairs of nodes, then E has high betweenness centrality. This means E plays a critical role in controlling the flow of information. Even if E does not have many connections, it can still be very important. This type of node is often responsible for connecting different communities. Removing such a node can fragment the network. This makes betweenness centrality very useful for detecting strategic influencers. I have another example here where it's the same node as up here. I copied it 2 times. In this scenario, I removed node A, which was here. We can only see one fragment, even though I removed only one node. On the other hand, I removed node E, which was here. Now I have 2 fragments. This means E has high betweenness and A has low betweenness. Now I will explain PageRank, which is a more advanced and realistic method for measuring influence in a graph. PageRank was originally developed by Google to rank web pages, but the same idea applies directly to social networks. The key idea behind PageRank is the following. Not all connections are equal, and a node is important if it is pointed to by other important nodes. This creates a recursive definition of importance. Let's take this example. We have 2 users. Let's say that user A is followed by 100 random users, and user B is followed by 5 but highly influential users. Even though A has more followers, B might actually be more influential. PageRank captures this difference. Now, to model this mathematically, PageRank simulates a random user moving through the network. Imagine a user randomly browsing the network. They start at a random node, let's say this one. Then they follow outgoing edges randomly. Over time, some nodes will be visited more often than others. The nodes visited more frequently are considered more important. So for example, here, this node has been visited 30 times, this one 19. So since 30 is greater, this node is more important. At this example, multiple nodes point at B in both cases. This means B accumulates importance. Now, in this scenario, node B points to node E. And here, node B points to both E and F. So B passes some of its importance to outgoing nodes. In this case, since B is only pointing to one node, E gets all the importance. And here, in this case, it's pointing to 2. So each one of those nodes will get 50% of the importance B has to offer. Now, if B had many outgoing edges, each one would receive less influence. PageRank is not just counting connections, it distributes importance across the graph. So each node receives less importance from incoming nodes, receives importance from incoming nodes and passes importance through outgoing edges. This creates a flow of influence. At each iteration, a node receives a fraction of the importance from every node that points to it, and the amount received depends on how important those nodes are and how many outgoing edges they have. In this example, let's say node A here has importance of 10 and node B has an importance of 8. Assuming each node offers 50% of the importance it has, so C accumulates 5, which is 50% of A, and 4, which is 50% of B's, which leads us to 5 plus 4, which is 9 total importance. However, PageRank has computational challenges. In a very large network, the number of nodes is massive and the iterations are expensive. So real systems use optimizations and approximations. Despite this, the core idea remains the same. Importance flows through connections. Now I will compare the three centrality algorithms side by side to highlight how each one defines importance differently. Degree centrality measures how many direct connections a node has. A node with many connections is considered popular, but this does not guarantee real influence. Betweenness centrality measures how often a node lies on shortest paths between other nodes. This identifies nodes that act as bridges and control how information flows across the network. PageRank measures importance based on incoming connections from other important nodes. A node becomes influential if it is connected to other influential nodes. These three methods highlight different types of importance. Degree identifies popularity, Betweenness identifies control over communication, and PageRank identifies true influence based on network structure. In social media terms, users with many followers have a high degree. Users connecting different groups have high Betweenness, and users followed by influencers have high PageRank. So each algorithm captures a different aspect of influence, and real systems often combine them to produce a more accurate result. Now I will connect these algorithms to real-world systems. In social media platforms, the entire network of users and interactions is modeled as a graph. Each user is a node, and actions such as follows, likes, or shares create edges. These platforms analyze this graph continuously. For example, when a post is published, the system needs to decide how widely it should be distributed. If the post originates from a user with a high influence, the platform is more likely to promote it to a larger audience. This decision is not random, it is based on graph analysis. Degree centrality helps identify users with a larger audience. Betweenness centrality helps identify users who can spread content between different communities. And PageRank helps identify users who are trusted or endorsed by other influential users. These metrics are often combined into a ranking system. For example, a user might have many followers, but if those followers are inactive or not influential, their overall impact is limited. On the other hand, a user with fewer followers but strong connections to influential users may have a much higher impact. This is why PageRank style approaches are widely used. Beyond social media, these same concepts apply in other domains. In cybersecurity, graphs are used to model networks of devices and connections. Centrality algorithms helps identify critical nodes that, if compromised, could affect the entire system. In transportation systems, graphs model roads and intersections. Algorithms identify critical routes and optimize traffic flow. In recommendation systems, graphs connect users to content. These systems use graph structure to suggest relevant items. This shows that graph theory is not limited to academic problems. It is a core tool used in real-world, large-scale systems. Now to conclude, graph theory provides a structured way to present complex systems as networks of nodes and connections. By modeling social media as a graph, we can apply centrality algorithms to analyze influence. Degree centrality identifies highly connected users. Betweenness centrality identifies users who control the flow of information. PageRank identifies users who are truly influential based on their position in the network. Each algorithm captures a different perspective of importance. Together, they provide a deeper understanding of how information spreads in the larger networks. These concepts are widely used in real-world applications, from social media to cybersecurity and recommendation systems. Understanding these algorithms is essential for analyzing modern data-driven systems and solving complex network problems.